Okay, so now we're going to do the turbulent boundary layer. So I like doing these sort of similarities in my head a lot to show I'm always doing really the same thing. So remember before, this was sort of the thing we did. For internal flow, right, we drew a diagram of a single straight pipe, right, and then for laminar, we could come up with the velocity distribution as a function of r. So this would be sort of laminar case. This function could then be used, right? So then u of r gave us a bunch of things, like it gave us the flow rate in the pipe. It could give us this v bar in the pipe. It could give us a v maximum in a pipe, right? And these sort of fundamental quantities, then these could be used, right, for friction factor, right? So then these could be used for a friction factor or equivalent lengths and things, or quantities like that. All right, bigger. So this was the laminar case. And then for the turbulent case, what was the thing? We couldn't do this part to get this function. So we got this sort of experimental or empirical approximation for u of r, and then everything was the same after that. We just got more complicated equations because of that, but it followed the same story, right? So that's exactly what's going to happen for the internal case. So let's go back now for, the external case. So then for the external case, we're going to see the same thing. Same thing's going to play out, right? What we did before, we took the simplest case. This is the long flat plate, right? Okay. Okay, we added some assumptions, a big one being that I know the boundary layer is a lot less than the length of this plate. We got scale equations. And this gave us then for really a laminar case, this gave us this equation here. So we could do the same process, and now we got two things where we could figure out sort of velocity distributions and delta distributions. Really, this one's the one that's mattered a lot. But then this could be used to then use that to calculate right. That gave us then, using these quantities, this could then give us these engineering quantities, right? And then I'll show you more how it is, but then essentially it's these quantities right here is what give you then coefficients of friction. Much like your Darcy friction factor, you had to use these fundamental engineering qualities, and we get this, and then you can calculate a drag force too. So in the last one, I actually should have put head loss. So what do you think is going to happen? Because this is a laminar. Well, in the turbulent case, exactly, it's still going to be some experiments, data, and approximations to give us this, and it's the same story past there. But this is its own lecture, because this will actually show you how you go from these functions like this to get those like 0.64s and those 1.3s, those just random coefficients, it seems like, those numbers. Using the turbulent case, you can really see where all that calculation comes from and where those constants are coming from. So, unlike internal flow, we also knew from an internal flow, right? Right, there's a critical Reynolds number. So 2100, 2000, your decision. Some people say 2000, but 2100 would work too. So here, an external flow, just from experiments. I mean, this one comes from experiments too. Don't think that you can just derive that 2100. This has a different critical number. This critical number is a lot bigger. It's huge. It's big. 5 to the 10 to the 5. So that's right. That's 1, 5 years. So much bigger, but the same process where you're tripping from a laminar flow to a turbulent flow happens. You just have a different critical Reynolds number. There's something that happens with boundary layers that you can clearly see. So we say then that the Reynolds number is less than this. We are laminar. And if the Reynolds number is more than this, we go turbulent. Right? Turbulent meaning all the same processes we kind of do with pipe flow, where there's more mixing involved. If you put dye in there, there's just a huge amount of mixing that happens in there. You get eddies and swirls. It's fundamentally a three-dimensional phenomena, but we don't need to know the details of turbulence. We just know that there's below and above. And later, there's some transitional range that we care about as well. So one idea of a boundary layer that I always think is kind of a sad story. And that is, all boundary layers are then going to become turbulent at one point, because, right, how do you calculate a Reynolds number point-wise? So it's x. So here, this is my x, this is my y. Okay? So if this grows and grows and grows and grows and grows, right, it's just linear with x, that means eventually it's going to hit that critical and it will go turbulent. So what you get is this region right here. Don't know what happens there. These are the regions now. So you have the laminar, which maybe you could think of as some x, and then here's sort of in region range, right? So here you can just see as x grows and grows and grows, and you still have this constant u naught, because that's just always constant. That is your free stream velocity. That doesn't change this time. What's changing now is how far along the plate you go. So there's this interesting phenomenon with boundary layers that all of them eventually will become turbulent. Why do they become turbulent? It's very subtle questions that you'll take graduate level classes and maybe you can give some reasoning to that. But it's a hard question of like, right, I mean, the transition's a funky one. The mechanisms, I think, are people just have tons of reasonings of why this happens. But I think you can just look at the Reynolds number, accept that there's a critical one, and see like, okay, well, if this x gets too big, I will surpass my critical, and then I'll become turbulent. So that is just sort of a, we can't, just like how an internal flows. Most flows that you're going to work with are internal. Same with the boundary layer, even worse. They're just all going to become turbulent, so we can't throw them away. So now that you all are kind of pros, I would say, I'm just going to cut to the chase on this one and and here's what you get. We're going to make, right, you really just get another Moody chart for these, for this coefficient of friction, right? The scale, I think I wrote this down. So this is about, scales in the book, it's like 0.014. It goes all the way down to about like 0.002. So here, and then what you get is this sort of where this is a roughness value over an L of a plate. This is your fully rough. This is like 10 to the 9. This is 10 to the 4 or something. And then there's a this is a transitional range, right? It's just a Moody chart that we're going to make again, right? So it's even has the same look, and there's reasons for that. I mean, really, right? Entrance lengths sort of affect the boundary layers as well, but so we're going to come up with more equations for the turbulent boundary layers. You already have the laminar ones to get this. Essentially, you already have the power law for that to plot it. So we're going to make more equations. Just like you had the Colebrook equation, you're going to have ones for other flat plates. And that's all of these. And we'll even have roughness values that you can calculate. So extra credit, make this plot on Excel with all the equations and make yourself an you call it external Moody plot or a skin friction plot, but that friction coefficient is very important. So, right, what's our goal in external flow? Keep that in your head always. Well, I want to calculate the drag force or frictional drag force, and the way I do that is this. No, I just don't know this thing. You use graphs for that, right? So very, very similar, right? Remember we had head loss, what we did? It's just this. So I hope you're getting to see just how common these things are, right? So the big thing is there's kind of two parts of these things. These parts are just bookkeeping. Right? These parts right here are just sort of parameters that I know, right? And then really all the work we've done in these classes are to get these values, right? So this takes thought, intuition, math, right? Charts. You got to figure out what these friction factors are. The only difference is that internally you just use Darcy. It's just a lowercase f. Here, the coefficient of friction, skin friction, is a C of F, and there's another one next lecture that will be coefficient of like drag, which is a pressure form drag. But right, you just totally see the identical behaviors of these things. It even has a velocity squared in there. The only difference is this is a force, this is a head, or this is units. So the units are different too. But right, so don't be too scared about where this stuff is headed because you've already done all this stuff before. You already know the mechanics of how to calculate, right, or the process of what you're doing. You're searching for friction factors, and then you're getting forces out of that, getting a drag force. That'll help you get a power force as well. So let's go through, and then we're going to see and define then. This is a definition of our friction factor. So this is just going to create this. I'm just rearranging what I had before. I've done nothing but rearrange. So I'm going to write this as an integral formulation now too. This is for a flat plate going along the plate. X is along the plate. So I'm integrating from 0 to an L along the plate. This is the same. Okay, so this is really, you always can go back to this definition of what the friction factor is and gives you an integral formulation of what it is. So now you see, right, this is the thing, right? This is, all of that work was really, what on earth do I sub into here? Right, so then if I can figure out some function of shears at the wall as a function of x, I can actually calculate out what the coefficient of friction is, regardless if it's a flat plate. This is all done analytically for the flat plate. That thing's been solved to death, but the process is the same for any object. You would just do it in a computer, and you would have to do it. But what methods do we have to figure out what T tau W is? Well, there's the simple way, which involves that momentum thickness, right? So simple way is actually doing this approximation right here. We got here Why was this simple? I went over this last lecture, but this is simple because I have a definition for what the momentum thickness is, and I can just plug into it some u of y. Okay? I have the freedom to just plug in some sort of symmetric function or something that at least satisfies those boundary conditions that, right, I can plug in any function as long as this is true. As long as at 0 I have no slip, and as long as I approach some boundary thickness, the delta, the boundary layer thickness, I will reach here. So you could plug that in and you can always get this. The harder way is actually just the definition of shear at the wall, right? Here is actually what Blasius did and what you will do. This is just what shear at the wall is, right? That's the definition of shear at the wall, right? Viscosity and the gradient as you go over the wall at 0. Okay, so this is hard though, because to actually get this, you need to know exactly what u of xy is. Right, the x of y. So this is going to come, right? This has to come, right? This has to come from the boundary layer equations we did in the early part of lecture 7, right? This means you have to actually solve, right, the BL equation, right, the boundary layer equations, right? You use something called a similarity. Use a similarity variable techniques, and that's just, right, so that's not in this class. We have this one. And really, this is also true for the laminar case, but I just want to highlight just for the turbulent cases that we're just doing the same thing. We're just jamming some u of y's in that definition and going with it. Okay, right? So let's remember that for here, okay, so this is the definition of the momentum thickness, and I should pull